Hey everyone, in this video we're going to talk about the tangential and angular descriptions of motion, and how exactly they tie into circular and rotational motion. This topic can get a little confusing, so let's review how everything is related and introduce a few more things. First, we'll review the difference between circular and rotational motion. Then we'll talk about the circular motion descriptions, the rotational motion descriptions, and then converting between the tangential and angular descriptions. At the end, we'll do a summary of the main points. Before we start, what do we mean by description of motion? Let's look at this car driving around in a circle. The motion is what the car is doing, what's happening in the real physical world. The description of that motion is how we're choosing to describe, measure, or study the motion of the car. The description of motion includes the axis, the units, and the positive and negative directions that we choose so that we can describe this motion in a way that's useful. Based on the description that we choose, we get some variables and equations that we can use to study that motion, do some math, and solve problems. The car doesn't care what description we choose, it's going to do the same thing either way. The reason we're distinguishing between these two things is because there's more than one way to describe a given motion. Depending on the situation or the problem we're trying to solve, we might choose one description or another, and we might need to convert from one description to a different one. Now let's quickly review the difference between circular and rotational motion. We're talking about an object's motion here, not the description of motion. With circular motion, an object follows a circular path centered on a point that is some distance away from the object. With rotational motion, an object is rotating about its own center, a point that lies on the object itself. We could say that the car on the left is translating through two-dimensional space, while the record on the right is not translating, it's only rotating. The car on the left is in circular motion, but if we could look at one of the wheels and ignore the car, we would see that the wheel is in rotational motion. We've seen that a record is in rotational motion while it's being played. But imagine a small fly is sitting on the record. The fly traces out a circular path, so the fly is in circular motion while the record is in rotational motion. The Earth orbits the Sun once a year, and from this point of view, the Earth is in circular motion around the Sun. At the same time, the Earth rotates once a day around its own axis, so if we only look at the Earth, it's in rotational motion. So those are a few examples. The terms circular and rotational are only referring to the type of real physical motion. Now, let's talk about the descriptions of motion that can be used for each one. We'll start with the circular motion descriptions. Circular motion typically uses the tangential description of motion. That's what we used in the video on circular motion. The tangential description means we're focusing on the path of the object around the circumference of a circle, and the direction of that motion is always tangent to the circle. These are the variables and equations that we use, and the units represent length. Now imagine we draw a line between the center of this circle and the car, which follows the car as it moves. When we look at it this way, we find that circular motion can also use the angular description of motion, because the object sweeps out an angle as it moves. So even though the car is an object in circular motion, it's possible to describe its motion using angles, and we can use the units, axis, variables, and equations from the angular description of motion. Here's the two descriptions side by side. The car is doing the same circular motion in each case, but using the angular description on the left, we'd say the car moved to an angular position of 240 degrees, and using the tangential description on the right, we'd say the car moved to a position of 80 meters, based on that axis. You might be wondering why anyone would want to describe the motion of this car using angles. Even though this car is moving around on its own, it's more common for things that travel in a circle to be attached to something that's rotating, like the fly sitting on a record. Also, this will be useful when we learn about periodic motion later on. Here's another example that highlights the difference between these descriptions. The yellow car and the red car are in circular motion on two different tracks. The yellow car is on a track with a radius of 20 meters, and the red car is on a track with a radius of 40 meters. If we use a line to follow the motion of the cars, we can see that both cars have the same angular motion. They both sweep out the same angle in the same amount of time, so they have the same angular velocity. We could also say they both travel a full revolution, 360 degrees, in the same time. However, the cars have different tangential velocities, so the drivers in each car are seeing different speeds on their dashboard. The red car is on a track with a bigger radius, so its circumference is bigger and the road is longer. If both cars travel one revolution in the same amount of time, and the red car covers more distance, then the red car has a greater tangential velocity. On the flip side, here's an example where the cars have the same tangential velocity, but different angular velocities. The driver in the yellow car is driving the same speed as the driver in the red car. But since the yellow car is driving around a smaller circumference, it drives around its track, 360 degrees, in less time, so it has a higher angular velocity. Even though the tracks have different lengths, or different tangential distances, they both cover the same angle of 360 degrees, or in SI units, 2 pi radians. This is why cars want to take the inside path or hug the inside of a curve during a race. If the two cars are driving at the same speed, the yellow car will complete a lap in less time because it's taking a shorter path. It's following the path of a circle with a smaller circumference. So those are some of the ways we can describe circular motion. Now, let's move on to rotational motion descriptions. Rotational motion typically uses the angular description of motion, like we did in the rotational motion video. With the angular description, we're placing an imaginary line on the object and watching how the angle of that line changes over time. These are the variables and equations that we use for the angular description of motion, and the units represent angles. Like we mentioned earlier, what if a small fly is sitting on this record while it's playing? The record is in rotational motion, but the fly is in circular motion because it's following a circular path. From the fly's perspective, it's like driving a car around a circular track. We're using a small fly as an example because the fly represents a point on the record. So we could say that a point on a rotating object can use the tangential description of motion because that point is in circular motion. That means we can describe the motion of the fly using the variables, equations, and units of the tangential description of motion. We can measure the distance the fly travels using a unit of length, like meters or centimeters. We already knew that circular motion uses the tangential description, so why is this important? Well, since the motion of the fly is linked to the motion of the record, we can say that a rotating object and a point on that object will both have the same angular descriptions of motion. If the record goes through one revolution, so does the fly. In fact, all points on a rotating object have the same angular motion. This is why we could place the line anywhere on the record, because all points on the record rotate together. As an example, now we have 3 flies on this record. Because the flies are all on the same rotating object, they all have the same angular velocity as the record itself. Fly A and B also have the same tangential velocity as each other, but fly C has a slower tangential velocity. Why is that? It's like the example with the cars. Fly C is traveling along a circular path with a smaller circumference, so it's traveling less distance in the same amount of time. But fly A and B both travel along a path with the same circumference, so they have the same tangential velocity. It might seem weird that 2 points on the same object could be traveling at different speeds. Their angular speeds are the same, but because they follow different circular paths in the same time, their tangential speeds are different. This is an important point, so take a moment to think about it. It's like the cars on different tracks that happen to be traveling at the same angular speed. They have different tangential speeds, and the car on the outside is traveling faster. It just seems weird that the flies have different tangential speeds because they're on the same object. So, we're finding that an object's distance from the center of rotation makes a difference. We call the distance between the circumference and the center of a circle the radius, and it turns out that we can convert between an object's angular motion and its tangential motion by using the radius. With that in mind, let's move on to the final topic, converting between tangential and angular descriptions. Let's think about how we might do this using an example. This car is in circular motion. During a period of time, the car travels both an angular displacement, delta theta, and a tangential displacement, delta s. If the angular displacement is pi over 2 radians, what's the tangential displacement? Put another way, what is the arc length that corresponds to an angle of pi over 2 radians? We can see that the car traveled 1/4 or 1/4 of the way around the circle. If we did the math, we would also find that pi over 2 radians is 1/4 of 2 pi radians, the number of radians in a full circle. So if the angle is 1/4 of a circle, then the arc length would also be 1/4 of a circle. If we knew the circumference, we could find 1/4 of that to get the arc length. So to solve this, we're going to need the radius of the circle. If the radius is 5 meters, then the circumference would be 2 times pi times 5 meters, which is 10 pi meters. Usually, we can't tell what fraction of a circle we're dealing with, so let's calculate that first. If we start with the angle, theta, which is pi over 2 radians, and we multiply that by the relationship of 1 circle equals 2 pi radians, then the radians will cancel out, and we find that the angle is 1/4 of a circle. Now we can take that fraction and multiply it by the circumference. But let's continue using unit relationships. So we'll multiply 1/4 of a circle times the relationship of 1 circumference per 1 circle. We just found the circumference, which is 10 pi meters. Now the unit of circles will cancel out, and we get 10 pi over 4 meters. That's about 7.85 meters in decimal form. So that's the arc length, or tangential displacement, delta s, that we're looking for. To recap, we found what fraction of a circle the angle theta represents, and then we multiplied that fraction by the circumference to get the arc length, because the angle and the arc length represent the same fraction of a circle. But what if we were given a different angle and radius, and we wanted to do the same thing? Let's simplify the work that we did to find something that applies to any angle and any radius. First, instead of calculating the fraction of the circle and then multiplying it by the circumference, we could have just multiplied the first part by the circumference. Radians and circles would cancel out, and we'd get the same answer. Next, instead of multiplying the angle, pi over 2 radians, by the relationship 1 circle per 2 pi radians, and then 1 circumference per circle, we could combine those into one relationship. 1 circumference corresponds to 2 pi radians, because they both correspond to 1 circle. So that's a lot less stuff to write. Now let's replace the values with variables. Using this general formula, we can plug in an angle in radians, a radius in meters, and we'll get an arc length in meters. If we remove the units, we get this simple equation. And in fact, this is the equation for arc length, although we usually write it like this. What would happen if we plug in 1 radian for the angle theta? R times 1 is just r, so the arc length equals the radius. That's actually the definition of a radian. It's the angle swept out by an arc length that's equal to the radius. What if we plug in 2 pi radians for theta? Then we get an arc length of r times 2 pi, which is the equation for the circumference of a circle. So this works for angular and tangential displacements. What if we wanted to convert from an angular velocity to a tangential velocity? Let's say this car is driving around the same circle with a radius of 5 meters and an angular velocity of pi over 2 radians per second. What's the car's tangential velocity? We could come up with an equation the same way we did before. If we take an angular velocity, omega, in radians per second, and multiply it by the relationship of one circumference, 2 pi r meters, which corresponds to an angle of 2 pi radians, then the 2 pi would cancel out, the radians would cancel out, and we'd be left with a tangential velocity in meters per second. So the radius times the angular velocity gives us the tangential velocity. This will be our conversion equation for velocity. Let's test it. If we plug in 5 meters for the radius and pi over 2 radians per second for the angular velocity, the equation tells us the tangential velocity will be 5 pi over 2 in meters per second. Why does this equation also work with velocity? Let's think about it this way. We know from before that an angular displacement of pi over 2 radians corresponds to a tangential displacement of 5 pi over 2 meters. If the car travels those displacements in 1 second, then we're just dividing the displacement by seconds to get the velocities. This works for angular and tangential acceleration too. Now let's look at everything together. On the left, we have the equations for the tangential description of motion, and on the right is the angular description. Now we have equations that we can use to convert between the two. If we take the angular variable and multiply it by the radius of the circular path, we get the tangential variable. It's important to remember that for this to work, the angular variable must use radians. So if it uses degrees or revolutions, we have to convert to radians, radians per second, or radians per second squared before plugging it in. As long as the tangential variable and the radius use the same length unit, things will still work, but it might be good practice to only use the SI units. To wrap up this section, let's look at some examples with a car driving around a circle with a radius of 20 meters. The tangential and angular values are linked, and their relationship depends on the radius. If the car's angular position at a certain time is 2 radians, then the tangential position would be 2 times 20, or 40 meters. If the car travels a tangential displacement of 60 meters, it also travels an angular displacement of 3 radians. In this case, we take delta s and divide it by r to get delta theta. If the car's angular velocity is 1 radian per second, the tangential velocity would be 20 meters per second. If the car speeds up, both velocities would increase. And if the car slows down, both velocities decrease. If the car's velocity is constant, then both the tangential and angular acceleration are 0. If the car speeds up and its tangential acceleration is 10 meters per second squared, then its angular acceleration would be 0.5 radians per second squared. And if the car slows down, the tangential and angular acceleration would both be negative. Again, the tangential and angular motions are linked together if they describe the same object. The difference is that tangential describes the motion around the circumference in terms of length, and angular describes the motion around a circle in terms of angles. So that's everything we're going to cover. What should we be expected to know from this video? Motion and the description of that motion are two separate things. The motion is what the object is doing in the physical world, and the description is how we choose to study that motion. The terms circular and rotational refer to two different types of physical motion. Circular motion is when an object follows a circular path, and rotational motion is when an object rotates about its own center. Circular motion typically uses the tangential description of motion. However, circular motion can also use the angular description of motion because the object sweeps out an angle as it moves. On the other hand, rotational motion typically uses the angular description of motion. But a point on a rotating object can use the tangential description of motion because the point is in circular motion. Also, all points on the same rotating object will have the same angular motion. However, those points will have different tangential motions if the points are different distances from the center. Finally, if we want to convert between the tangential and angular descriptions of motion, we can use these equations, which are based on the relationship between an arc length and the angle swept out by that arc. If we multiply the angular value using radians times the radius of the circular path, we get the corresponding tangential value. Thanks for watching, and I'll see you in the next video.